Hi, this is the second session of the business analytics course, and we are going to discuss probability distributions. Most importantly, we are going to discuss how are we going to fit a distribution to a given data. So, first of all, let us do a recap. What are probability distributions? We already have discussed it in other courses, but what do we think, what do we recall as probability distributions? So, essentially probability distributions are some kind of a statistical model that that shows possible outcomes of a particular event or course of action that event may take, right. So, essentially probability distributions for a discrete random variable may look like all the possible values of the random variable along with the corresponding probabilities that the random variable will take on that particular value. And for a continuous distributions, we generally represent that by a density function. For example, if you recall, we may have said that the x axis represents the values of the random variable, the y axis represents the probability, and for a discrete random variable we will say that what is the probability that x takes on a value equal to 1, and then we would have said some probability. What is the probability that x takes on a particular value 2, and we would have said some probability, right. So, this is how the probability distribution looks like for a discrete random variable. Now, for a continuous random variable, we still have the same format, which essentially means that x axis still represents the value of the random variable, y axis represents some form of probability, but we do not say probability. We usually, if you recall, we say density function, right, density function, and then we would have drawn something like this for potential values of the random variable x. What is the difference here? In the earlier diagram we had discrete probability masses because the random variable was discrete. Here we have continuous values of the random variable, and therefore we can't really say that there is a probability mass sitting at a particular point. For example, let us say that we are still talking about x taking on a value equal to 2. We can't say that this is the probability, this is only the probability density, right. So, we only talk about density, and for density we need a small interval to actually define some probability, right. So, you recall all of that, right. So, the focus of this session is not to re-describe density functions and probability distributions. The focus of this session is to go one step beyond and say that, well, I have data now, and how do I fit some distributions to data, or what do I do with that data, right. So, for example, let us say that in academic settings we hear this quite a lot. So, grades of a course follow a normal distribution. What do I mean by that, right? So, what do I mean by that? Essentially grades, right. So, random variable is grades here. So, grades, so grades out of 100, let us say. So, random variable is grades, and then it follows a normal distribution, which essentially means that we are going to follow, assume that this is a nice bell shaped curve, right. And then some people are going to get very high marks, some people are going to get very low marks, unfortunately, and there are a whole bunch of people who are going to be in between, right. So, that's what we mean by normal distribution. Once again, the y axis represents the density, right. So, this is just a recall, right. Or sometimes in the business settings we may say something like this: sales next month are expected to be uniformly distributed, right. So, what do we mean by that? So, I may say that sales can be as low as $100,000, sales can be as high as $200,000. This is sales next month, sales in the next month, right. So, it can be $100,000 or it can be $200,000, but instead of assuming a normal distribution, so right on x axis is sales, here is your 100,000, here is your 200,000, and we are saying that it is not uniformly distributed, right. So, you know what a uniform distribution is. Once again, y axis represents the density, right. So, these are essentially probability distributions: normal distribution, uniform distribution. We have taken 2 examples of continuous distribution, but you get the idea, right. So, that's how we define probability distributions, that's how we use probability distributions, right. So, now how are we going to go about using data, right. So, let us say that I have business data that I have collected. The business data may be about sales volumes, the business data may be about the defaulters on loans, the business data may be salary hikes that the employees got in a particular year. It may be about any business context. For this kind of a data, right, we can directly use the data and use it in our simulations, right. There is no need to fit any distributions. This is typically called trace driven simulation. So, let us say that we have collected sales volume over a period of time. Let us say we have a monthly sales volume for the last 3 years, which essentially means that I have 36 values in my data set. So, instead of first fitting a distribution to the 36 values and then using the distribution in my further analysis, I can directly use these 36 values in my analysis. So, if I want to simulate, I will simulate directly using these 36 values. This is generally called trace driven simulation. The second method is to actually fit a theoretical distribution. What do I mean by theoretical distribution? Theoretical distribution is all these things that we spoke about earlier: normal distribution, uniform distribution, binomial distribution for discrete, Poisson distribution for discrete, right, exponential distribution for continuous. These are all theoretical distributions. So, what we may do is for the sales volume data that we may have, sales volume data that I may have, I may try to fit, quote unquote, fit a distribution to my data, right. And obviously, I can't simply say, okay, normal distribution fits very well. I have to go beyond that, and I have to actually check whether the fit that I have assumed is actually good. And I am using these terms in a very deliberate way because these are precisely the technical terms which are going to be helpful later on, right. So, we always are going to say we are going to fit a distribution, we are going to check how good is this fitment, right. Now, let us say that our business data that we have collected is a particularly tricky data set, and it does not fit very well with lot of theoretical distributions or the other way around. Most of the theoretical distributions do not fit to our data. What are we going to do? Well, it is not the end of the world. Instead of trying to fit a already available distribution like a negative binomial or a double exponential, instead of fitting those kind of already available distributions to the data, what you can do is we can actually create our own distributions, right. I mean, this is like making rules as we go along, typically Kelvin category, but we create our own distributions, and those distributions are called empirical distributions. So, the sales volume data that I already spoke about, using that data, we say that, well, what would be the distribution where these 36 values could have come from. So, using these 36 values, we build our own empirical distribution and use that distribution in our future analysis, right. Now, what are these empirical distributions? Have you discussed empirical distributions in your earlier courses? Most probably you have. So, let us quickly recall that, right. So, what are these empirical distributions? Empirical distributions are essentially distributions built from the data that we already have collected, right. We are not fitting a distribution to the data, we are actually building a distribution from the data that we have collected. Please notice the difference, right. So, let us go beyond. So, how does one build a distribution? First of all, what are the building blocks? When we say we are building a distribution, how do we build a distribution? Right. For example, normal distribution. Let us take simplest, right. Normal. If we were to say that I want to characterize a normal distribution, what would we need to characterize a normal distribution? Well, we will need the building blocks. So, what are these building blocks? So, essential building blocks of any distribution are the density functions, the distribution functions, right. And we may also want to define some moments, the first moment around the mean, the second moment around the mean, which can be built using density also, right. So, we have to estimate these parameters. So, essentially defining a distribution means identifying a density function or a distribution function. From the density function, you can identify the building blocks like moments around the mean, mean, standard deviation, and so on, right. Let us take an example of how to build an empirical distribution. So, let us say the data is ungrouped. Let us say that we have collected x1, x2, x3 values. So, the x1 value, x2 value, x3 value, and let us say all the way to x36. These are our 36 sales volume data for 36 months in our data set. Now, what we are going to do is we are going to arrange them in a ascending order. So, x1 value was the first value that was recorded, which was the first month, right. But what we are going to do now is we are going to arrange it in a ascending order, where the smallest value is called x bracket 1, okay, x bracket 1, second smallest value is called x bracket 2, and the largest value is called x bracket n. In our case, x36 may not be the sales volume in the 36th month, it is actually the maximum possible sales volume that we have found in our data set. Okay. So, so these are called rank order statistics. Let us not worry about rank order statistics. So, once we have arranged the data in an ascending order, you can actually define a distribution function in this way, right. This is not our own creation. These are definitions are usually available in any standard statistics textbook. Alright, so this is one way. I mean, this by no means we are saying that this is the only way of defining a distribution function. Now, once we get a distribution function, we all know how to get a density function, and from density function we know how to get moments around the mean. This is for ungrouped data, right. This is for ungrouped data. So, this is for ungrouped data. Now, if the data were grouped, meaning that I only know that in this interval I have 10 values, in the other interval I have some 8 values, in some other interval I have some 5 values. If I have group data, so let us say that intervals, we define k intervals, right. So, we have intervals, k such intervals, and I know that in each interval I have some n1, n2, n3 values. So, in the first interval I have n1 values, second interval I have n2 values, third interval I have n3 values, kth interval I have nk values, and that gives me my total sample size of n, right. So, what we can do is we can create a piecewise linear function g using this definition, right, where each g of aj, right, is essentially proportion of the sample proportion of the observations up to that point, right, up to that interval. So, once again a very non-unique way of defining a distribution function. Once again notice that this is a distribution function. Why do I know that this is a distribution function? Because the value value lesser than the smallest value is 0 and the value beyond the highest value is 1, which is a typical definition of a distribution function which goes from 0 to 1, right. And once again our usual methods are going to kick in, where we have a distribution function, from there we get the density function and so on. So, these are examples of how we can build empirical distribution. Let us go back. Why are we saying that why did we build these empirical distributions in the first place? We are saying that we have data. We have collected data. That data may be for any context, it may be sales for our marketing data, it may be financial analysis data, it may be stock price data, right, it may be stock price data. So, let us say that a technical analyst wants to analyze, wants to invest in the stock market. Now, what are technical analysts? Well, figure out, why don't you search for it, and then we will describe it in the next sessions. So, technical analysts, let us say that they want to invest, and for their investment decisions they have collected stock prices for the last 3 months. So, and let us say that I have actually tick level data. Tick level data means I get data not every hour of a trading day, I may get data every minute or every second, right. So, I have huge data sets, I mean that data set will be huge. Now, I want to decide whether the stock is going to move up or move down, right. Now, I have to predict whether I have whole massive data set of all the stock prices up to that point for the last 3 months, and now I am saying tomorrow the market opens at 10 o'clock, what is going to be the opening price of this particular stock for which I have collected data. Now, how are you going to go about doing this? We said the first option is to just use the 3 months of data that you have collected, plain data that you have collected, use the same values. That would be called trace driven simulation. Second approach would be for the 3-month data that you have collected, why don't you fit a distribution, and there has been enough and more research on what is a good fit for a stock price data. Obviously, everybody wants to crack that problem, right? And very clearly that I have not solved that problem, because if I had cracked that problem, I would not be sitting here. It's already 11 o'clock. I would be using my distribution and playing with the market. So, you can fit a distribution for the 3 months of data that you have collected, and I have whole bunch of candidate distributions available: normal distribution, uniform distribution, log normal distribution, Y-bull distribution, the full family, right? Not the full family, the full forest. So, and the third way is the 3 months of data that I have collected is for a fairly weird stock. It doesn't none of the distributions amenably fit the data, and therefore I want to define my own distributions, and therefore we got into the empirical distributions, right. Therefore we got into the empirical distributions. So, these are two examples of how to build empirical distributions from the data that we have. Now, let us go back and go to step number 2. What if I want to fit theoretical distributions? How do I go about doing that, right? So, before we do that, let us quickly take a look at how these 3 approaches compare with each other. Usually, approach 1, which is using the plain 3 months data, is usually used to validate the models, right. We already have a model, you already have the output, and you want to validate whether that output is correct or not. So, what you do is you push this 3 months of data into your model, and your model generates an output, and you compare that output with the reality, with the existing system, which is what happens tomorrow, check and whether that matches, right. So, essentially trace driven simulation is mainly used to fit to validate a model that you already may have built using something, right, some different approach. So, you have some prior knowledge how to build models for stock prices, you have already done that. Now, you want to check whether that model is correct or not, and therefore, you feed into that model this 3 months of data. Whatever comes out of this model should match with what happened in reality, or should come close to each other. The drawback of this approach is you are going to test your model only with the data that you have collected. So, for example, going back to the sales volume data, you only have 36 values. So, your model is going to be tested only using the 36 values that you have actually observed and fed into the model. That may not be enough, right, that may not be enough. Even with the 3 months of minute level data on the stock prices, let us say the stock price was fairly stable during these 3 months, there was no turbulence in the market. So, how will you test whether your model works very well in the turbulent period? Now, this data that you have collected will not give you that simulation, because this data was collected from a fairly stable stock period, right, a stock market period. So, those are some of the problems. Approaches 2 and 3, building your distributions or using a theoretical distribution kind of avoid these problems. Because what you can do is, once you have built a distribution, you can generate values from those distributions which are not restricted to the 36 values that you have actually observed in your sample, right. So, compared to approach 1, I would say approach 2 and 3 are preferable that way. However, if you can actually find a theoretical distribution that fits your data, I would generally avoid building empirical distributions. Therefore, I would say that theoretical distributions are preferred over empirical distributions. The problem with empirical distributions is very similar to the problem that we have for approach 1. Now, when you build a empirical distribution from the data that you have, the distribution, the shape of the distribution is completely governed by the data that you have used to build the distribution functions. Remember, your distribution functions are built from the data that you have. So, the shape of the distribution will be completely governed by your data. Now, once again, if the data is of a particular pattern, then quite likely that the distribution will be biased towards that. The other problem is the distribution that we build usually are restricted by the smallest and the largest value. So, here the distribution is 0 for all the values lesser than the smallest value that you have observed. The distribution is 1 beyond the maximum value that you have observed in the sample, which may not be true, right. This is the smallest value that I have observed in the sample, does not mean that sales cannot be lower than this. This is the maximum value that I have observed in the sample, does not mean that my sales cannot be more than that. However, the distribution that you build using this data will pretty much say so. The distribution that we have built will say that probability of finding a sales volume lesser than the smallest value is 0, and indirectly speaking, probability of finding a sales volume bigger than the maximum value is again 0, almost 0, right. So, so those are the problems. So, we are still not able to go beyond whatever we have observed in our sample, right. So, that is those are the problems with yeah. So, if you want to test the validity of our system from an empirical from a data that comes from an empirical distribution, we may have problem because we cannot simulate values which are outside of the range that was fed into, right. So, those are some of the issues with empirical distributions. Now, there may be some compelling reasons for using a particular theoretical distributions. For example, let us say that you have data about reliability. Now, reliability engineering has a very high importance for Weibull distribution. So, for any data that comes about distribution or the reliability, I would like to test whether it fits the Weibull family, right. Is it coming close there? So, those cases also, yeah, those cases also, I mean, theoretical distributions, why not test it before? So, yeah, so those are the that's the difference between fitting a theoretical distribution and fitting an empirical distribution.